Okay, recording in progress. Share the screen here. Okay, so we're continuing on with 9.2. So we did the slope fields, and heads up for the quiz on Friday, I'll more than likely give you a slope field. Okay, so you'll take one of these differential equations, make the table of 49, right? It goes from -3 to 3 for both x and y. And you'll fill out the table of 49 and then translate that into slope field. Okay. So you'll be making on the quiz something like that, or like that, or like that, or whatever. Okay. And you'll make a table sort of like that. All right. So today we're going to do Euler's method. Euler's method on page 595. Okay. So here's the idea. You're given a differential equation. Let's say y prime equals x plus y. We can make a slope field, right? You can make the chart and so forth and go from there. And they give you an initial condition. Okay. So based on that information, we're supposed to guess or predict what happens after that. Okay. Okay, so we will see what happens over here. Whoops. Okay, so here's a true solution curve. We don't know what it is offhand, let's say. Okay. We drop the particle here. By the time it reaches 1, okay, where are we going to be? Are we going to be here or here or here or here or here or where? Okay, so that's basically what's happening. If you're given one of these slope fields, okay, so I dropped a particle, let's say over here. Can we predict what will happen by the time x comes out to be 3, let's say? Is it going to be here or here or wherever? Okay, so how do we do that? We don't know the solution curve necessarily. So our first guess is this. Okay, so remember, every point in the xy plane has an associated slope, one of these things. Okay, well, the absolute easiest thing to do is say to myself, okay, I have a slope, right? Let me just take that slope and go in a straight line until I reach x equals 1, and that's going to be my guess. Okay? It's probably not going to be a very good guess in general, right? So again, the true solution is like this. We have one of these things. You have a slope field. You have an initial condition. Okay, we're going to estimate what happens by the time we reach 1. We're estimating y of 1. Okay. So if I just say I'm going to go in a straight line, probably not too good. They call it the first Euler approximation. Okay. Then we do what we normally do in calculus. Suppose I say, well, let me chop the interval from 0 to 1 into 2 pieces. So I go 0, 0.5, and 1. So that means I'll go in a straight line. Notice it's the same original slope. Go in a straight line until I get to 0.5. And then I stop and get a new slope. Okay. I plug in this point to the differential equation and then recalibrate. And that sends me off in another direction. And you can see by doing that, I get a little bit closer to the true curve. And we play the same game in calculus. Suppose I chop it up into 4 pieces, 0.25, 0.5, 0.75, 0.1. Okay. We start off with the original same slope, go until I reach 0.25, stop, recalibrate, get a new slope, sends me in another direction. Get up to 0.5, stop, recalibrate, go in another direction. To 7.75, stop, recalibrate, do it again. So by taking n equals 4, I've chopped the interval up into 4 pieces. I get an even better approximation. And as you might guess, if I let delta x approach 0 and n approaches infinity, okay, I mean, the picture would start looking like this, if I can, right over here, right? It would end up looking more like that, where you have tiny, 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 tiny delta x, and at each one of these points, you recalibrate, recalibrate, recalibrate. Well, after a while, the approximation is so good that it looks like you're practically hugging the curve, and then you get closer and closer to the true value. Okay. Of course, if once you start to getting n equals 1,000,000, there's no way I'm going to make you do that by hand. Okay. The most I'm willing to let you do by hand is maybe about 5. That's probably good enough. If you know how to do it for 5, you know how to do it for 1,000,000. Then, of course, you have a computer do that, right? You can program a computer very easily to do this computation and get a better approximation and so on. Okay. Now, the text gives you their way of doing Euler's method. It's correct. Okay. So if you want to use it, you can use it. But I'll show you my version, which I think is easier to understand. Obviously, I'm biased. I'd rather do it my way. But let me see what's happening. But you can see on page 596, here they have different values of n, which means they chop it up into so many pieces. If you chop the interval up into one piece, then you're just going in a straight line, right? N equals 1. That's like n equals 1. This is like n equals 2. And then you did n equals 10 and so on. Okay. And a different step size. Step size is your delta x. Okay. And so what's going on here? They're showing you the approximation gets better and better and better and better. It approximates the exact solution the more pieces you chop up the interval into. Right? So if you look at these different colors, the ones that are further down, farther away, let's see, this bottom one, n is only 2. The next one looks like n equals 4. And the one way at the top, I'm not sure what the n was, but you can see the approximation gets better and better and better. All right, so now let me show you my version, and that's how I would prefer that you do it. So let's look at problem 19. Use Euler's method with each of the following step sizes to estimate the value of y of 0.4, where y is the solution of the initial value problem, y prime equals y of 0 equals 1. Okay. So what's this h stuff? H is the same as delta x. H is delta x. In Calc 1, when you were doing the definition of the derivative, limit h approaches 0, f of x plus h minus f of x all over h, right? Well, h is really a delta x. It's a tiny little change in x. So this is delta x. That's delta x. That's delta x. Okay. So now let me give you my version of the introduction to this stuff. Okay, so I'm mimicking what they said in the text. Suppose you have a differential equation y prime equals x plus y. In general, y prime is f of x, y. I know you're not used to that notation. Say, hey, there's 2 letters here. Yes, and when you get to Calc 3 being multivariable calculus, you will have not just f of x or f of w and so on. You have 2 variables inside, f of x, y, or maybe 3 variables, f of x, y, z, or even 4 variables, f of x, y, z, t, t being time. All right, so differential equation that looks like y prime equals stuff with x and y. An initial condition, where do I drop the particle? Y of 0 is 1. And we want to estimate some future value, estimate y of 2. And don't get scared by that y of 2. It means the same thing as f of 2. Y of 2, f of 2, same thing. All right, so first some fundamentals. Y prime, derivative means slope. So for this section, I'll interchange y prime with m, slope of the tangent line. M Well, from algebra 1, it's delta y over delta x. Change in y divided by change in x. Multiply both sides by delta x. Delta y equals m delta x. So this is a slope or y prime. Okay. If you need, just put this on your cheat sheet. Okay. If we were meeting face to face, I'd make you guys memorize it. But it's not that hard to memorize. I mean, even in algebra 1, you memorize y equals mx plus b, right? Y equals mx plus b. So just put deltas in here. Delta y is m delta x. All right, then these two equations, you can put these on your cheat sheet. But if you just reason it out, the new x is the old x plus delta x, right? And the new y is the old y plus delta y. So I'm playing this game, I'm moving along somewhere and so on. Say, what's my new x value? Well, you take the old x value and then add delta x to it, right? What's my new y value? I take the old y value and tack on or subtract delta y. Setting you up for Calc 3, you would have z, x, y, and z, right? The new z value would be the old z value plus delta z, very natural, right? So in Calc 3, you have x, y, and z, right? You have 3 dimensions. All right, so key ideas that we're going to do over and over and over here are delta y equals m delta x, and then x new is x old plus delta x, y sub new is y sub old plus delta y. Okay, so now problem 19, y prime is equal to y, and y of 0 is equal to 1. Estimate y of 0.4. Okay, that means this. This picture is not drawn to scale. I didn't want it to be a scale. Okay. Here's my differential equation. We can make one of these fields, right? In fact, this one would be pretty easy because it doesn't depend on x. So you make this thing, but we're not really going to do it. We drop the particle at 0, 1. By the time we reach 0.4, where are we? All right, so 19AI, they say h, which is the same as delta x, is 0.4. So they want us to go 0.4, which is the easiest case, but it's probably the least accurate. This is the next harder, but it's more accurate. The hardest, but even more accurate. But just like anything else, right? The more you put into it, the more you should get out of it, right? In order to get increased accuracy, you got to do more work. All right, so we're estimating y of 0.4. That means by the time x is 0.4, where are we? So we're going from 0 to 0.4. The step size is 0.4. That means you're just going in a straight line segment straight over there, right? So I start at 0, 1. What's my slope? This differential equation says the slope is just simply the y value. So the y coordinate is 1. So slope is 1. Then I keep using delta y is equal to m delta x. So m is 1 times 0.4 is 0.4. What's my new x? Old x plus delta x. So I started at 0. The step size is 0.4. So now I'm at 0.4. What's my new y value? Y new is y old plus delta y. What was my old y value? 1. My delta y is 0.4. So if I used to be at 1, I add 0.4. So now I'm at 1.4. Okay, so in this simple case, very easy to compute, but it's probably not that accurate. Y of 0.4 is roughly 1.4. So I'm done with that problem. Delta x was 0.4. N is equal to 1. Probably not that accurate. Okay, now part A, II, the h, which is the same as delta x, is now 0.2. That means chop the interval up into 2 pieces. So here, I quote unquote chop the interval into 1 piece, which means I don't do anything. So once I get my slope, I just go in that straight line segment until I reach 0.4. And where am I at? I had to compute my delta y. It was 0.4. So I rose 0.4. Okay, I was at 1. I rose 0.4. So now I'm at 1.4. Probably not that accurate. So we're saying now, okay, we're going to take the interval from 0 to 0.4, chop it up into 2 pieces. So by the time I reach a 0.2, I will stop and recalibrate and get a new slope, as you can see here. Okay. You're saying, where am I getting these numbers? We'll see. So delta x is now 0.2. So I start at 0, 1. The slope is still 1. I plug into the differential equation. 1 right there. Y prime is 1. Delta y is m delta x. Okay. You can put that in your cheat sheet if you wish. So m is 1, delta x is 0.2, 0.2. So what's my new ordered pair, my new point? 0.2, 1.2. You say, how did you get that? I started at 0, 1, right? Delta x is 0.2, so that means I went from 0 to 0.2. Delta y was also 0.2. I started at 1, so that means I'm now at 1.2. So my new point is 0.2, 1.2. How do I find a new x? Take the old x and add delta x. How do I find a new y? Take the old y and tack on delta y. So I'm now at 0.2, 1.2. I stop and recalibrate a new slope. So I'm going to shoot off in a different direction. Okay. In the original case, slope was 1 all the way through. Right. So I just went in a straight line with a slope of 1 from 0 to 0.4. Now, halfway through the problem, I stop and get myself a new slope, and that'll hopefully draw me closer to the true curve. So I take 0.2 and 1.2, plug it into the differential equation. Y prime is just y. So my new slope is 1.2. So the picture is kind of like this. I know it's exaggerated, but to show you that I stop and go at a new direction, and this new direction, this new angle, would get me closer to the graph. So what is delta y by formula? Delta y is m delta x. Again, where does it come from? Since m from algebra is delta y over delta x, right? Multiply both sides by delta x. Delta y equals m delta x. So 1.2 is the new slope times the delta x 0.2, 0.24. This is the new delta y. So what's the new point? 0.4, 1.44. Again, you say, how did you get that? Okay. I was here. Delta x is still 0.2. For any one particular problem, the delta x stays the same. It never changes. So for this problem, delta x stays 0.2. I was here. I add 0.2. How do I get to 1.44? This is the old y. This is the delta y. So I was at 1.2. I rose 0.24. So after I've risen 0.24, I now am at 1.44. Right. So for the second part of the problem, y of 0.4 is approximately 1.44. So my new guess is the function value by the time I reach the 0.4 is 1.44. And side note, what was it after 19 was 1.4. And this one's a little bit higher, as we would hope it to be. All right, then part A, I. It's the most amount of work, but it's probably going to be the most accurate. H is 0.1 is delta x. So I get a new calibration at 0.1, 0.2, 0.3, 0.4. And in this particular case, I drew it like this because I know each time I stop and get a new slope, it's going to recalibrate to be something steeper. So if it becomes steeper, it gets closer to the true graph in this particular case. Okay, so delta x, h is 0.1. So I go to 0.1, stop, get a new slope. Then I go to 0.2, stop, get a new slope. Then I go to 0.3, stop, get a new slope. And then I finally reach 0.4. it will definitely be the most accurate, but it's going to be the most amount of work. All right? So we start at 0, 1. You have the same initial condition in each case, 0, 1. Slope is 1. Notice the starting slope stays the same. Well, that makes sense. If I were to draw, this slope field, the slope's not going to change, right? Like, let's just slope, suppose this slope is -1. It doesn't matter if I chop the interval into 2 or 3 or a million pieces, my beginning slope is still going to be -1, right? All right, slope is 1. Delta y equals m delta x. Notice I keep writing that. Delta y is m delta x, delta y is m delta x, and so on. So slope is 1, but delta x is 0.1. So my delta y is 0.1. That now leads me to the point 0.1, 1.1. Okay, and you might say, how did you get that? Okay. Always going back to this. What's the new x? Take the old x, add delta x. What's the new y? Take the old y, add delta y. If we were to go down to Calc 3, what's the new z? It's the old z plus delta z, right? In 3 dimensions. But right now we're in 2 dimensions. Okay, so how do I get this point? The old x was 0. Delta x is 0.1. So now I'm at 0.1. And by the way, the x coordinate is already predetermined. So even before I start, I know I'm going to have 0, 0.1, 0.2, 0.3, 0.4. Those are fixed. I don't even have to think about that because my delta x stays 0.1 for any one problem. Any one problem I do, the delta x is fixed. So I already know it's going to be 0, 0.1, 0.2, 0.3, 0.4. The calculations are to figure out the delta y's. Okay. So how do I get to 1.1? Okay. So the new y is the old y plus delta y. That's why we have to keep computing delta y. So the old y was 1, right? Delta y is 0.1. So if I was at 1, I've risen 0.1. Now I'm up to 1.1. Stop, do it all over again. So it's a lot more work, a lot more calculation, but you're going to get more accuracy. What's my new slope? 1.1. How do I know? From the differential equation. This is a fairly easy differential equation, but the next example I'm going to show you, if I have time, it won't be that easy. So my new slope is 1.1. So it got a little steeper. And the next one will be steeper still. And the last one will be steeper still. Again, delta y is m delta x. Well, delta x never changes. 0.1, 0.1, 0.1, 0.1. Okay, but the m changes. So the new m is 1.1. And 1.1 times 0.1 is 0.11. So notice I've risen a little bit more than my first iteration, my first try, 0.11. Okay. So now I'm at 0.2, 1.21. How did I get that? The new x is the old x plus delta x. The new y is the old y plus delta y. So I used to be at 1.1, right? I've risen 0.11. That means I add them up. My new y value is 1.21. So this point right here is this thing, 0.2, 1.21. Stop, get a new slope. In this case, the slope is easy. The slope is the same as the y coordinate. So the new slope is 1.21. So I'm getting steeper. I started off with a slope of 1, got a little bit steeper, 1.1. Now it's a little bit steeper still, 1.21. And just jumping ahead, the next, it's 1.3 something. It's even steeper still. So what's my delta y? M delta x. Put that on your cheat sheet if you wish. And all this stuff. So let's see, that times that is 0.121. So what's my new point? 0.3. Again, the x's are already predetermined. Even before I start, I know it's 0, 0.1, 0.2, 0.3, 0.4. And the picture even gives it to you like that. The delta y's are the ones that are the ones in question. So 1.331, you say, how did you get that? I was here, right? I've risen this much. So after I've risen this much, I'm now here. That plus that. By the way, I say rise, you could fall. I'll show you an example later where the delta y's are negative, in which case you wouldn't actually be rising, you'd be falling. And I got one more time to do it, because by the next time I'll be at 0.4. So steeper still. So slope starts off at 1, and then a little bit steeper, 1.1, and then 1.21, and then 1.331. So one more time, m is 1.331, just because of the differential equation says y prime is equal to y. Don't think that that's always going to be the case. Okay? And the next problem I'll show you, you don't just copy the y coordinate. In this easy case, that's true, but that won't be true when I do the next one where it says y prime equals x minus 2y or something like that. Okay, delta y is m delta x. So my new m is 1.331. Delta x stays the same, 0.1. Right, 0.1, 0.1, 0.1. Okay, so 0.1331. That's my new delta y. All right, new x value is 0.4. Old x plus delta x. So the new y is the old y plus delta y. So I was at 1.331. I've risen 0.1331. So you can add them up. If I've risen this much, then now I'm at 1.4641. So my new guesstimate, y of 0.4, is 1.4641. A little bit higher up. Okay, so let's look at the progression. If I have n equals 1, I chop it up into one piece, 1.4. 2 pieces, 1.44. 4 pieces, 1.4641. Okay, now part B, which you can see I didn't write very much at all, because I didn't have to. Let's see. Where am I? We know that an exact solution of the initial value problem is y equals e to the x. Okay, don't worry about drawing anything. Never mind about drawing it, but I will just talk about it a little bit more. Okay, and we're going to skip C. So, yeah, just cross this off. And for part B, let's forget about all that. We'll stop right here and show a little bit more about what happens. Okay, an exact solution is y equals e to the x. Where'd you get that from? Well, is this differential equation true? Y prime equals y. The derivative is the same as the original function. We know that's true for e to the x, right? What's the derivative of e to the x? E to the x. So that's definitely true. The derivative is equal to the original function. And y of 0 equals 1 means when you plug in 0, you get 1. That's definitely true. Okay, so we were guesstimating y of 0.4. Let's actually plug in e to the 0.4, and it's roughly 1.4918. Okay. And I very rarely had to touch my calculator, but that's okay. E to the 0.4, 1.4918. So this is just to show you, yes, indeed, this was the true value. Let's look at the progression. N equals 1, 1.4. N equals 2, 1.44, a little bit better. N equals 4, 1.46. The true value is 1.49. So yes, the bigger the n, the closer we get to the true solution. So I'm guessing the problem's now finished, but if you were to chop it up into 1,000,000 pieces, of course you wouldn't want to do that by hand. You would just simply program the computer to do that. it would more than likely get very, very close to 1.4918. If I did the same thing, chop it, chop, into a million pieces, let your computer, grind it out on its CPU, and it would probably be very close to 1.4918. Okay. So this is our first example of Euler's method, but frankly, the differential equation was too easy. Y prime was just equal to the y value. So let me do one that's a little bit harder now. Okay, so that was 19. Okay, the only other ones we have are 21, 22, 23, and 24. Okay, so that's 4 more. I'll do 2 of those. All right, so I was going to show you, let's see, 22, which is going to be much longer. And it's a harder differential equation. Actually, this is not what I had in mind. This is not what I have in the book. So yeah, I'm going to give you 22 star. Sorry, not quite what we have here. Tell you what, for 22, change it to 22 star. In other words, this is the problem. Don't do the one that's in the book. Okay, so your problem 22 that you're responsible for is what I'm calling 22 star. Like that. Do 22 star. What is 22 star? This one. You don't have the answer in the back of the book anyway because it's an easy problem. All right, y prime equals xy minus x squared. Y of 0 is 1. Estimate y of 1. Delta x is 0.2 and n equals 5. So I have to do 5 calculations. I'm going from 0 to 1. Delta x is 1 over 5, 0.2. So I'm going to go 0, 0.2, 0.4, 0.6, 0.8, 1. Okay. I've already done the calculations. In fact, you can see I even messed up sometime. But I'll just fly through it because you can punch in a calculator as well as I can, or better. So there's 5 iterations. ITERATIONS. Iteration is doing something repeatedly. How many times you do something repeatedly? Okay, so I plug in here now. So 0, 1. Put a 0 here and a 1 here and a 0 here. You get 0. So m is 0 times 1, x times y, minus x squared, 0 squared, which is 0. You can't get much better than a slope of 0. So delta y is m delta x. 0 times 0.2 is 0. So if my delta y is 0, I'm now at 0.2, 1. Right? Automatically, the x's are set. 0.2, 0.4, 0.6, 0.8, and 1.0 or 1. The y's are the ones that are harder to compute. Now, the next one is going to be of substance. I'm now at x comma y. Plug into the differential equation. 0.2 for x, 1 for y. So 0.2 times 1 is 0.2 minus 0.2 squared. Okay. Punch it in the machine, save time, I've already done it, 0.16. So that's my new slope. Delta y is m delta x, 0.032. It does get a little bit sloppy. So my new point is 0.4, 1.032. Where'd I get the 1.032? Old y plus delta y. You can also say old x plus delta x, but you already know the delta x doesn't change at 0.2. So it's automatically 0, 0.2, 0.4, 0.6, 0.8, and 1. Those are predetermined. The y's are not predetermined. Okay, the calculation gets kind of weird after a while. So I got to figure out a new slope. How do I find the slope? Plug in the differential equation. Remember, y prime means slope. So I plug in x, y minus x squared. It's a little bit more clumsy. 0.4 times 1.032 minus 0.4 squared. I think that's what I meant there. Minus 0.4 squared is what I meant. Okay, I did it already. 0.2528. So I've risen 0.2528. Oh, I'm sorry. That's my new slope. That's nothing like that I've risen. That's a new slope. Then delta y is m delta x. So 0.2528 times delta x of 0.2, 0.05056. That's the amount that I'm rising. So now I add these two guys together. Old y plus delta y. The delta y tells you how much you're going to rise. So I was here, I've risen 0.05056. So after I've risen this much, I'm now over here. 0.6 comma 1.08256. Stop, recalibrate, get a new direction. So m is equal to, plug in x times y minus x squared. So x times y minus x squared. Punch it in the machine, 0.289536. Okay, I'll save time, just said, I've already done it. That's what you get. Delta y equals m delta x. So here's my m. Delta x stays 0.2. So the problem, it stays 0.2 all the way through. And that times that comes out to be this thing, 0.057, blah, 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 blah. That's my delta y. That's how much I'm going to rise. So I'm at 0.8. I'm almost done. Now, how to get this weird thing? The new y is the old y plus delta y. So I'm at this height. I've risen this much. So I'm now at 1.1404672. And finally, at last, I got to do it one more time. M, plug in a differential equation, xy minus x squared. So that times that minus 0.8 squared. Punch it in the machine, I got 0.27, blah, 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 blah. And once again, delta y is m delta x. Here's my new m. M means slope. Y prime means slope. M delta x, punch it in the machine, 0.0544, blah, 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 blah. So the new x is definitely 1. We already knew that ahead of time. How to get this mess? The new y is the old y plus delta y. So I used to be at 1.14. I've risen 0.05. So now I'm at 1.19, etc. Right, so that's my final answer. I would say y of 1 is approximately 1.1949. And that's pretty much about it for that. Okay, so you can see there's a lot that's involved in these problems. Okay, then looking at the time that we have, it's 10:02. Yeah, I think I've done enough. I wasn't going to show you the last one. I don't have enough time, but I'll save it for tomorrow. So 21, let's see. Yeah, Mr. Stewart did not change that problem, so I will do that in its entirety tomorrow. But for 21, the delta y comes out to be negative. So I wanted to show you at least one example where the delta y's are negative. So I keep saying how much you're rising, or the graph has risen so much, but here you're not actually rising, you're actually going to fall. So it'll be falling because the delta y's turn out to be negative, but that's okay. That's definitely a possibility. Okay, so I'll show you one more of that tomorrow. And then I'm ready for 9.3, which is the last section leading up to the test a week from Friday we have here. Okay. All right, so that's all I have for today, folks. Let me stop the share and see if you have any questions. So anybody have any questions? Otherwise, we're going to call it a day. And so tomorrow I'll do that last one problem and then I'll start 9.3 hopefully. Okay. All right, any questions, please? All right, that'll do it for today then, and we'll see you all next time. Okay, bye.
All right, take care, Professor. Thank you.